You guys are ready? You can start.
We are ready right now. We're doing infinite series. What is an infinite series? Well, it's not a finite series. A finite series would be like if you have like 10 up here and you have like k equals 1 and you have like 2x, and then that would end at 10. That's not what an infinite series is. Infinite series would be where you have infinity. That's an infinity sign up there, and it just goes on forever. It's kind of a simple concept to grasp, but there's a lot more complicated stuff as you get more into it, and they're actually very useful if you didn't know that.
Okay, so this will become evident once I do a demonstration of Zeno's paradox. So if I throw this marker there, did it hit the wall? It did. How did it hit the wall? Well, there's a theory to that. See, Zeno, using infinite series, tried to prove that objects can't ever truly reach a destination because, so for example, if I'm the marker and I'm going towards that thing, I first have to go half the distance, right? So I go like half the distance. And then from here, I have to go again half the distance of this to there, which would be an infinite series. So I go here, then I have to go again half the distance, so I go here. And eventually, I'm just going half the distance again, but I'm never actually going to truly reach the wall because you just keep going half distances. So with that, this cartoon is really funny because it's like, yeah. And some people try to use that to prove that if you give someone a head start on a race, you will never truly win because you will never be able, if you're here and the person's there, you will never be truly able to catch up because first you have to go half, then you have to go halfway more and halfway more.
Yeah. Theory is you first have to go half before you can go the whole.
Yeah.
But that's not true because if this marker did that, it would never hit the wall.
Which it does.
It does hit the wall, so it's a paradox. All right.
Yeah.
Well, I'm going to stop you for 1 second. I just want to say that what you could say at this point is we're going to use Zeno's paradox to say that time is never run out. Because even if I say 1 minute, you can say, well, it means we have
30,
half of a minute, and then a quarter of a minute, and then an eighth of a minute, eventually, well, we just keep going.
Exactly, yeah.
Okay, it's crazy.
It is crazy.
Okay, so this is something really cool. You can actually calculate the sum of an infinite series if it converges. And the equation for that would be, so the sum is...
Use the black one. The black one.
Yeah, I have this one.
Thanks. So the sum is the first term divided by 1 minus r. And what r is, it's the constant multiplier. So for example, if I have a series that goes like 1, and then 1/3, and then 1/9, and then 1/27, the constant multiplier here would be 1/3, because it says times 1/3, times 1/3, times 1/3. So I would do 1 over, because 1 is the first term, over 1 minus 1/3. And then you would calculate that out, and you find that it would be 1.5. So that's kind of cool, because we have all these different equations to calculate the sum of arithmetic sequences, but when it comes to geometric infinite series, this is really cool for finding the sum of them. And then you can also, there's a way to use infinite series and this equation to make a repeating decimal into a fraction. So if I had the repeating decimal 0.272727 repeating, so this is basically 0.27 plus 0.0027 plus 0.00027, right? This is kind of like Zeno's paradox if you think about it in an abstract way. And then you would take the second term and divide it by the first term. And if that result is less than 1, you get that, and it would be 0.01. If that result is less than 1, then you can calculate you can make this into a fraction using the equation. So then you would take, using like the first term over 1 minus this value, which would be kind of like your R value in the other equation. So you would do 0.27 divided by 1 minus 0.01, and you find that to be 3/11, which is very cool. Okay.
Alright, I'm going to talk about applications of infinite series because it'd be a little silly to just talk about abstract things without relating it. So they're actually very useful in calculating infinite numbers. Like if you look at this one, going out to infinity, 1 divided by k minus 1 factorial. That's a 1, by the way. If you calculate this out all the way, you get like 1 divided by 0 factorial, 1 factorial, and it goes out and it's like 1 plus 1 plus 1 half plus 1 sixth plus 1 24th, all the way out. And if you...
Can you write some terms out for us then?
Absolutely. 1 plus 1 plus 1 half plus 1 sixth plus 1 24th plus 1 1/20th plus 1 720th. That's how many terms I calculated it out to. Does anyone want to add those up? Maybe we can see what they equal. 1 plus 1 plus 1 half plus 1 sixth plus 1 24th plus 1 20th plus 1 720th. Yeah, I know, it's getting crazy in the tiny numbers, but there's a reason. What is it?
2.71805 about.
Do you know what that's similar to?
E.
Yes, it is basically E. If you take it out all the way, it gives you E. And that, when you think about that even more, that's really powerful. Something like this. To calculate a number like that, if you were, say, making a computer, you could either have the computer remember 1 billion digits of E, or you could have the computer remember that little formula that I put up, and boom, you have E anyway, that it can generate. Another one, a little more complicated, -1 to the k plus 1 over 4 to the 2k minus 1. And I'm just going to write a few terms of this. 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths. Now, it's a little more complicated. I'm just going to tell you what it equals. It basically gives you pi. And that's also really powerful because the ability to just choose how many digits of pi you want is pretty powerful. If you're NASA and you need 1 trillion digits of pi or something because you're going to like land on Jupiter for whatever reason with a rover and you need it exact, you can just plug this formula in and you have 1 trillion digits. Or if you're a little kid and you're just trying to get like the area of a circle, you just need like 6 digits. It's powerful. And once again, for saving computer memory, you don't need to put in all those digits, you just need the equation. That's pretty impressive. And there are even more applications of these. While this looks really complicated, and it is, I'm not going to try to explain the math behind it. It's a Fourier series. This is actually the inverse Fourier transform, so it's not the exact one. But you don't need to worry about that. You just need to know that these infinite series are used. They take things like this with these infinite series. They use them to calculate all sorts of things in the real world. They're used on condensing JPEG images on a computer. Instead of remembering each like color transition from red to blue to green, it can just create a little infinite series out of it, condense an equation into it, and that's how it puts them into such small little pockets to save memory. They're used in engineering, analysis of electric currents, analysis of sound waves, solving differential equations, electronically synthesized music, and also exponents and logs, because once again, when you think about an exponent or a logarithmic function, it does go out forever, approaching something like that. There you go. There you can see these infinite series are super powerful.
Thank you. Very good.
Does anyone have
Questions?
Eleanor.
Is there like a mathematical explanation for why Zeno's paradox doesn't work?
No, but there's a realistic vision.
Yeah.
That's why I said paradox.
I mean, people have been debating Zeno's paradoxes for a very long time. He has quite a few. But if you think about it theoretically, doesn't it make a lot of sense? I mean, if you have 1 minute of time, you have 30 seconds, and then you have...
Like, theoretically, it does.
It makes a lot of sense, right? And it's cool. Yeah.
Marielle, so if you sum the series, so let's say the distance is 2 meters, so it'd be 1 plus a half plus a quarter plus an eighth, right? So that's an infinite series.
Yeah.
And if you sum that 1 over 1 minus r,
Yeah.
that would be 2, because it's 1 over 1 minus 1 half, right? So that's 1 over 1 half, and that's 2.
It's the first term over 1 minus r.
Yeah, and the r is 1 half.
R is 1 half.
So 1 over 1 minus 1 half.
Would be 2.
Yeah. So I think you could probably prove it that way.
Oh, Zeno's paradox?
Yeah, right.
Oh.
Because it's summing an infinite series, and it's r is less than 1.
Yeah. That's
Really?
exactly right.
Oh, that's so cool.
That's exactly right.
Really cool.
Yeah.
That was my project.
That's
That's
why-
the only reason I know.
That's why it's a paradox. As Ben was saying, it's not something that has a clear, clean, crisp explanation. You can look at it in 2 ways. Infinity is like that too. The concept of infinity is both a concept and also a number. And it's not obvious how you should interpret that. It is paradoxical. You know, paradox concept. Anything else? I have one question. Is there anything else that you get, like if you sum an infinite series, you can get e and you can get pi. Is there anything else that you guys found that would happen if you summed an infinite series? Any other bizarre numbers or strange things that you could get? I don't know of any others. So, did you find any in your research?
I didn't find any offhand.
I mean, e and pi are very unusual numbers.
Yeah, there's
even
a lot
among
of
the rational numbers.
numbers.
They're called transcendental numbers. They're very unusual. And I thought maybe there's something else that, you know, or maybe you could sum something and get the square root of 2, or something like
Or
that.
could you get like B? At 1.61 made.
Yeah, you get that in a different way. You get that in a different way.
Like, is there?
Yeah, I don't know. Okay, well that was very good, you guys.